Let's now look at example 3 in our study of how to find a confidence interval to estimate a population mean value. So let me spend some time again to read example 3. National mean gas price on June 1st, 2020 was known to be within 0.05 of a sample mean at 99% confidence level, given that sigma equals 0.15. How large must the sample be to ensure this estimate? And after reading out the wording of the question, let's spend some time extracting the given information. So for given information, let me break things down one by one right here. So let's look for the usual thing, the common things. So the sample we have, the question we have here, we're looking at 99% confidence level. So we already had a known confidence level being 99%, or for computational use, 0.99. It's given quite clearly in the wording that sigma equals 0.15. So remind yourself again that this sigma is our population standard deviation value of national gas prices. So in other words, we can put that in our list of given information. Sigma equals 0.15. But now, anyone viewing this video must now pay attention to this last question right here. The ultimate question of this problem is asking, how large must the sample be to ensure this estimate? So that means in this problem, we are no longer finding the interval. We're not looking for the estimates. We're actually looking for how big the sample size. But what do I mean by we're not looking for the estimates? Because we actually already had the estimate. So what you need now to pay attention to is the term within 0.05. This term within 0.05, let me do a quick demonstration right here. But at this point of our learning, any confidence interval is in a form of some sample mean being up and down by a margin of error, add or minus the margin of error. So within 0.05, the term within 0.05 means from whichever the value our sample mean can be, it is going to be up and down by 0.05. So within 0.05 is another way of saying that we already had the margin of error being, so this is our margin of error being 0.05. This is our E value. And so on our list of given information, we now can list that margin of error is a given information. So margin of error being 0.05. So in that way, we don't need to use the formula E equals Z sub C multiplied with sigma over square root n for calculating our margin of error, because we already had margin of error. So we're not using the formula to calculate the margin of error. And so back to the question itself that I previously highlighted in yellow right here, but how large must the sample be? So that means our goal here is to find out how big is our sample size. I'm going to put a double question mark there. How big is our sample size? And so now we are ready for finding our answer here. So I briefly explained earlier, but now let me clearly explain it down here. But so at this point of your learning, there are two formulas for margin of error calculation. One of them is Z sub C multiplied with sigma divided by square root n for calculating margin of error. The other formula serving the same purpose is T sub C multiplied with sample standard deviation over square root n And so it could be a little bit of challenge to decide which formula being used in this problem right here. I would say the one we will be using is going to be this one. The reason being, this is always the formula that's ideally a lot more accurate. The only disadvantage of this formula is that we must be dependent on having a sigma value, but we already had sigma for this problem, so our calculation is ready. And besides, we actually know no information about our sample values, so this formula is not useful in this situation here. So now, in the formula that I previously chosen, margin of error is z sub c multiplied with sigma over square root of n. Note how we already had margin of error given, so we can substitute this value to the left hand side of this equation. Now if we're looking at this formula as an equation, then 0.05 is going to substitute for e on the left hand side. Z sub c can be calculated easily, and sigma value can be substituting for sigma, and we can solve for n. However, solving for n in this case takes some algebra, so I also recommend in this video a slightly different route in case anyone is not too comfortable with algebra. But from where our known formula here to calculate margin of error, we can now regard to this as an equation and algebraically rearrange this equation to arrive at a different formula. So rearranging this equation algebraically, I'm going to arrive at n equals z sub c multiplied with sigma over margin of error and square the entire quotient. This rearrangement of our equation now becomes a formula that's quite useful in our situation here, because now it serves as a formula to calculate our sample size as our goal of the problem. Allow me not to show the algebra steps, how I can rearrange this equation from the first form to the other form, but let me get straight into showing you how to use this final form of our rearranged equation as a formula here. But so looking into this formula now, then we already had margin of error given to be 0.05. So margin of error 0.05 will substitute for e in our new formula. We can easily calculate z sub c, and with our given standard deviation sigma equals 0.15 right here, we can substitute for sigma in our formula. So everything is ready. So sample size can be calculated by some z sub c, because I haven't found any z sub c at this point yet. Multiply with 0.15 and divided by 0.05, and that quotient is going to be square. So let's now spend some time finding z sub c. First step, 0.5 plus half of our confidence level, so 0.99 over 2. Calculation comes out to be 0.995, and this is referred to as some area left. The actual z sub c comes out by running the INVZ program, and this program only asks for area left, and this is where we're providing 0.995. With my INVZ on screen currently, 0.995 is the left area, and after running it, we're getting 2.575823 and a lot longer. So in 3 decimals, which is what I usually use for most of my video lessons, 2.576. So that is how we found our z sub c value. So now we're ready for our final calculation. sample size in our case here can be calculated by 2.576, that's our z sub c, multiplied with 0.15 and divided all that by margin of error 0.05, and this quotient is going to be squared. Final answer comes out to be 59.721984, and a lot longer. And again, I need to remind everybody that this answer coming out being a decimal is completely usual. It's just the way how the calculation is being set up as a formula. And there's nothing wrong with the calculator. But now this answer cannot be accepted as our final answer yet. So here's the reason. Sample size must be our sample size. Any sample size must be a whole value. The reason for this? A sample size usually represents the number of people in the sample, or in our study here, the number of gas stations that we are going through to collect our samples. So we cannot break a gas station apart to find a 0.72 of a gas station. We cannot break a person apart to find a 0.72 of a person. So rule of thumb is sample size must be a whole value. That's requirement number one. Another understanding quite important is that the larger our sample size is, the better estimate we've had. And so the intention of this answer now is that any sample size have to be at least 5972. So being at least this value and together with being a whole value, we are forced to round this to, so now our concluded solution for this, we're going to need to always round to the nearest whole value above. So in that reason, our final answer is rounded to 60. That is our final answer. And so in the way how I was making my reasoning and my explanation earlier, you may see quite a few textbooks over the web or on the market, or delivering the formula to calculate sample size, pretty much the same formula that we've been using. Let me now put that in a box here. But my version doesn't need to have fancy symbol, but quite a few textbooks give the same formula. That includes an extra symbol. And this symbol is to indicate that we need to round our answer that comes out from this calculation. We need to round that answer to the nearest whole value above. But really, I do not require any of my students to use this formula. What you need to remember is to run this main calculation formula, and your final answer must be rounded to the nearest whole value above.